Yeah, yesterday we discussed about the skill enhancement course 1, that is the remote sensing and GIS, GPS. And today we are going to discussing about skill enhancement course 2, that is geochemistry. In geochemistry, we have 4 units again. Just we'll discuss the outline of all these topics, but actually we have no time. The first one, it is a basic concepts of geochemistry. Second one is a periodical table. And third one is a composition of planets, meteorites of and Earth. Fourth one is analytical techniques. And when you come into the block 2, that is geochemistry 2, block 2, unit 5, geochemical cycle. Unit 6, so geochemical classification and distribution of elements. Unit 7, water quality parameters and water quality. And unit 8, it's analytical techniques. Yeah. Basic concepts of geochemistry in this one. The geochemistry definition. What it is a geochemistry? The geochemistry, actually, it is a geochemistry. It is a science which uses to study and the principles of chemistry, and it's explained to the mechanism behind the geological systems as Earth's crust and its oceans also. The geochemistry, it extends beyond the Earth and encompassing the entire solar system, and it has made important contributions to the understanding of various Earth processes. And geochemistry, it is emerged as a separate discipline after the establishment of a major laboratories as part of the world and began the systematic surveys of chemistry of rocks and minerals. Michael Clark noted that geochemistry, the chemical elements generally it is decreased in abundance as their atomic weights and increase, and summarize the work elemental abundance in the data of geochemistry. The composition of meteorites was investigated and compared to the terrestrial rocks as early as 1850. This was beginnings of a field in Cosmo Chemistry, and it has it was contributed much what we know about the formation of the Earth and the solar system also. In 1920s and 1930s, Goldsmith and associate members, they were formulated some rules to grouping of the elements. The scope of geochemistry, it is defined as a historical development of geology. Because the geochemistry as a formal discipline, it was relatively late in developing. It's related to subject areas, especially mineralogy and petrology often cover subject matter which might well fall within the area of geochemistry. And again, it's related to the environmental also. And again, it's playing a very important role in the mineral exploration and all those things. The geochemistry, it helps to understand the various earth processes, the principles of the distribution of the chemical elements in the lithosphere, hydrosphere, atmosphere, and biospheres also. The geochemistry, it is defined as a science. It's a concern with the chemistry of Earth as a whole and its of its component parts. And geochemistry, it deals the distribution and migration of the chemical elements within the earth rocks and different minerals, as well as the movement of these minerals in the soil, water, and space in the time. To properly understand the chemistry of the earth, it is important that we know as much as possible about the chemistry and the history of the sun and other planetary bodies in the solar system, as well as the chemistry of the stars and interplanetary and interstellar spaces. The geochemical methods for exploration, its integral components, the various techniques are available to modern methods for exploration and to prospecting and specialization of the techniques. The goal of every exploration method is to find two clues that will help locating hidden core bodies. Michael Clark definition of a geochemist. The Michael Clark, he explained, he was given a definition to the geochemistry. Each rock maybe it's regarded for a present purpose as well as chemical systems in which by different agencies the chemical changes can brought about. Every such change implies the distribution of equilibrium with the ultimate formation of a new system. Yeah, the studies maybe it is we see in a province of a geochemistry, and to determine what changes are possible, how it will be occur, where they will be occur, when they occur, to observe the phenomena, with to attend them, and note the final results, functions of the geochemist. For a geological point of view, a solid earth crust, it's a consisting of a major elements and the major chemical elements it has. And here, which takes place in maybe conveniently the classified of the three heads. The first one, it is a reaction between the essential constituents of the earth itself, and second one, it is a reaction due to the aqueous envelope, and third one, reactions produced by the agency of atmosphere. The goldsmith of definition. The primary purpose of a geochemistry, it is on hand to determine the qualitatively composition of the earth and its parts, on other to discover the laws and which control to the distribution of individual elements. To solve these problems, the geochemist it's a require a comprehensive collection of analytical data and terrestrial materials such as rocks, waters, and comprehensive collections and atmosphere. And there are some tasks in geochemistry. What we will do with the geochemistry? The main task of a geochemistry, it's saying that one, it is the determination of relative and absolute abundance of the elements and of the atomic species in the earth. Second one, it is the study of the distribution and migration of the individual elements in the various parts of the earth and in minerals and rocks also, with the object of the discovering principles governing this distribution and migration. Geochemistry has been defined as the historical development of a geology, because the geochemistry as a formal discipline, it was a relatively late developing relatively subjected areas, especially particularly if you can see in mineralogy and petrology. Often it's covering the subject matter which might well fall within the areas of geochemistry. The empirical and geochemical studies of element distribution on Earth's surface and have played the significant role in mineral exploration. The knowledge of geochemistry helps in understanding the various Earth processes, the principles of distribution of chemical elements in lithosphere, hydrosphere, atmosphere, and biosphere. There are some branches in geochemistry, let us see. The sense of geochemistry, it is applied in various fields to understand the Earth process, mineral prospecting, and environmental purpose, pollution studies in many relative fields also. The first one, it is applied geochemistry. The applied geochemistry, the principles of a geochemistry which have some practical applications to an aspect of a human endeavor, such as the preservation of the environment, health, waste disposal, and search for researches. We can apply this one into the inorganic, organic, and isotope geochemistry, and also geochemical process, which are included in the broad field of applied geochemistry. When you go into the applied exploration geochemistry, the exploration geochemistry, it's a concentrate the particular abundance and the distribution of migration of ore elements, or elements which are close associated with the ore, with the objection of a detecting over different deposits. The search of economic mineral deposits of petroleum is detecting by the abnormal concentrations of elements of hydrocarbons. Environmental geochemistry is concerned with the pollution of the superficial environment by industrial waste, metal and radioactive byproducts of nuclear reactors, including the natural and anthropogenic aspects. The hydrogeochemistry deals with the study of chemistry, ground and surface waters, particularly its relationship between the chemical characters of water and quality of a water and quantity of a water, which will be also you can study here. Medical geochemistry. The medical geochemistry is a new branch of geochemistry. It deals the methods of approaches, different geological fields, how it will be useful to human beings. And the branch of geochemistry looks the effects of geochemical process and geological factors and all those. Agriculture geochemistry. In agriculture geochemistry, the geological resources, what are required and what are the minor and major elements which are playing very important role in animal and plant nutrition. And the geochemistry, it is in public health, is concerned with minor elements in your food, drinking water, and their relation of human health. Aquatic geochemistry, it deals the study and pertaining the role of various elements in water bodies and how elements fluxes are exchanged through the atmosphere and terrestrial aquatic interactions. The biogeochemistry, it is a broad and diverse field into at intersection between the biology, geology, and chemistry that has largely developed a link between the geochemistry and ecology. The field of biogeochemistry involves scientific study for chemical, physical, geological, and biological process and the reaction with the govern the composition of natural environment, including the biosphere, hydrosphere, pedosphere, and lithospheres also. The Cosmo Chemistry. The Cosmo Chemistry, it is a deals the distribution of elements in their isotopes in the universe. And the isotope geochemistry, which is a deals the determination of relative and absolute concentration of elements in their isotopes. The organic geochemistry deals with the study process compounds which are derived from a living and once living organism. The photogeochemistry, the study of light-induced chemical reactions which occurs may occur among the natural components of Earth's surface. Rational geochemistry, including the applications to the environmental and hydrological and mineral exploration studies. History and development of this geochemistry. In geochemistry, it's basically the consensus of chemical elements, the discovered of recognition landmarks, which is to the history of a subject. Levaiser is the recognized 31 elements: oxygen, nitrogen, hydrogen, sulfur, phosphorus, carbon, chlorine, boron, strontium, argentinum, arsenic, bismuth, cobalt, copper, samarium, iron, manganese, hydrogen, molybdenum, nickel, arum, platinum, lead, ultramite, zinc, calcium, magnesium, barium, aluminum, sulfur. These are all elements, and arum, argentinum, cuprite, iron, lead. Tin actually it is a hydrogen, sulfur, and carbon are already known to the ancient world. So the last 2 decades, 18th century, saw the discovery of different elements like uranium, zircon, strontium, titanium, yttrium, beryllium, chromium, and tellurium. As of 2016, the confirmed elements are 118 from the element, and hydrogen 118 Augustinian. the first 94 elements which are occur naturally, and other remaining 24 americium to organicium. The 95 to 118 which are occur were synthesized in the laboratory of 94 naturally occurring elements in 83 years of primordial and 11 occurring into the decay of chains of primordial elements. So Clark was responsible for a vast and ever growing the output of analysis of minerals. Clarks and ores. The development of geochemistry in a new direction is greatly advanced by the established geophysical laboratory, Kernan Institute of Washington in 1904. The work of B.M. Goldsmith and his associated attained the world distinctions. So that after that, in many ways, in 1912, it is considered the critical date of the development of geochemistry. And after that, it is attributed that the Goldsmith insight that he not only realized the significance of the crystal structure and determination of geochemistry, but also it's a devised a plan of research that led to the maximum results on minimum time. Last 50 years of we have seen geochemistry developing coherent collections of actual data and scientific data. As per that geochemical cycle, it is individual elements as they thought according to that. Yeah. The most advances of geochemistry can be attributed to improvement in analytical techniques, the study of radioactivity during and after World War II led to the enormous improvements in elemental analysis by neutron activation and opened the opportunity for isotope studies and geochronometry by mass spectrometric techniques. Both of these are powerful analytical techniques, which continue to be improved, provide and us which better data on smaller geochemical samples. But this similarly, the same geochemistry is playing the very important role in mineral exploration. The mineral exploration point of view, various geochemical methods for exploration are available in nowadays. Geochemical prospecting of minerals includes any method of mineral exploration based on a systematic measurement of one or more chemical properties which are of naturally occurring material. The natural occurring material including rock, maybe soil or bossons or glacier debris, vegetation, stream, or whatever it is, stream or whatever sediment material, and again not only that one, water and water vapor. The main purpose of this measurement to discovery of abnormal chemical patterns and geochemical anomalies, it's related to the mineralization. The geochemical methods of exploration, which are integral components of various techniques, are available in modern prospectors. The geochemical surveys are more classified as a reconnaissance and detailed surveys. The purpose of this reconnaissance survey, it is useful for to search of a mineralogical to search of a large deposition of ore deposition of a ore in a particular area. After that, the completion of that one, the main aim of a reconnaissance survey is to determine the mineral possibilities of a relatively very large area and to eliminate the barren grounds and to delineate the areas of whatever interest. After that, suppose if you do the 1,000 kilometers, 1,000 squares of a kilometers are elevated during the geochemical reconnaissance survey, and finally we have a find only just a limitation area of ore deposits. That area only, if it has the mineralogical deposits, then we'll go to the detailed study for that one. So here, the advantages of geochemical techniques and hence this widely used in particular mineral exploration. And when you come into the detailed surveys, the purpose it is outlined to mineralize the ground and to pinpoint to the mineralized source with a greatest possible of precision. And then the application of detailed surveys, mostly it is restricted in a limited areas. The geochemistry in relation to the environment. Yes, must and should the geochemistry, every geochemistry point of view, it's a must and should internally it is related to the environment. Either maybe it is a natural or anthropogenic environment. The contaminants, maybe it is contaminated, presented in the air, and then implications for human health and environment. The environmental geochemistry, it is a provide a thorough understanding of controls of on the chemical quality of a surface and subsurface of waters, both pressure either polluted. The principles of environmental geochemistry which are applied in the study pertaining the environmental impacts on the soils, groundwater, freshwater, and atmosphere. And geochemistry in a earth process. Yeah, here we must and should we have to know about the that is a abundance of chemical elements. Abundance of chemical elements. We know that the principal distribution chemical elements we see that is a lithosphere, hydrosphere, atmosphere, and biosphere. The building blocks of a material which are having the chemical elements. Atoms with the same atomic number, but different neutrons which are called, we know that is isotopes. And the most unstable isotopes do not occur in nature. In a geochemistry point of view, the stable isotopes are used to trace the geochemical pathways and reactions, while isotopes are primarily used to date samples. The chemical behavior of an atom, its affinity for other elements, and the type of bonds it forms, it is determined by the arrangement of electrons in orbitals, and particularly the outermost, that means outermost means the valence electrons. These arrangements are reflected into the position of elements in the periodic table. Based on the position of the elements which falls into the group, like as a alkali metals, alkaline earth metals, and transition metals, semi-metals, halogens, and noble gases, lanthanides, and actinides. There are various differences. Geochemical cycles. In geochemical cycles, through a variety of physical and chemical processes will be involved, and the chemical elements which are change their own concentration and move around the in what we are called that is a cycle. That means here it will be changes, and it is a moving from one state to another state. Either maybe it is in the process of a physical process and the chemical process. And an understanding of these changes requires both the detailed observations and theoretical model. Geochemical model generally involves the feedback. It is the simplest case of a linear cycle, either the input or the output from the reservoir. It is proportional to the concentration of, for example, salt is removed from the ocean by formation of evaporites. And it's given the constant rate of evaporation in evaporate basins, the rate of removal of a salt, it should be proportional to its concentration. Solar system of elements. Here the chemical composition of a solar system, it's similar to the many other stars, and either side of the anomalies it can be assumed to have a form from solar nebula that had a uniform composition, and the composition of a sun photosphere, it is similar to the rest of the solar system. The composition of a photosphere, it is determined by fitting the February absorption lines in its spectrum to model of the sun atmosphere. By far the largest two elements of bifraction, the total mass are hydrogen 74.9 and helium will get the 28.3%. And remaining elements, it's contributing up to 1.3 only. So that here the some compared to the overall trend, lithium boron, beryllium and depleted, and iron, it is enormously it is enriched. Meteorite elements. In a meteorite elements, meteorites it's come under the different composition. But chemical analysis, it can be determined whether they once the planetesimal that will melted or differentiated. Chondrites are undifferentiated and have a round material mineral inclusions called chondrules. Chondrules. With the age of this 4.56 billion years, they date to your solar system. A particular kind of the chondrite has the composition as closely matches that the sun's photosphere, except for depletion of some volatiles like hydrogen, helium, carbon, nitrogen, and oxygen. And a group of elements, that is maybe it's a lithium, boron, beryllium, which are destroyed by nucleosynthesis in the sun. The chondrites, it's more accurate than for than for the photosphere. So it is generally used the source for chemical abundance and despite rareness. Earth crust, we know that the earth crust, the major composition of earth crust, it's having the oxides, chlorides, sulfides, and fluorides. And then for an important exception with that total number of any rock, it is usually less than 1%. Michael Clark has calculated a little more 47% of the earth crust. It's consisting of oxygen only. And it's a principle, it's a combination of oxides, which the chief are silica, alumina, iron oxides, and various carbonates. The silica functions principally as an acid forming silicates. If it is possible by rock analysis to say approximately what minerals that rock contains, but there are numerous exceptions to any rule. Mineral constants, we see in earth crust composition, it has 90% of the silicate minerals. And their abundance, it is the follows. Plagioclase for 39%, alkali for 12%, quartz 12%, pyroxene 11%, amphibole 5%, mica 5%. Clays minerals, which are also we see it's dust also 5%, and remaining silicate minerals, it's make up to another 3% into the earth crust. Only 8% of the earth is composed of non-silicate minerals such as carbonate, oxides, and other sulfides. Yeah, there are some trace metals in oceans. The trace metals, it's readily form the complex of major ions in the ocean. It's including the hydroxide, carbonate, and chloride. And their chemical speciation change depending on the whether the environment is oxidized or reduced. Trace metals with a nutrient type distributions are strongly associated with the natural internal cycle of particulate organic matter, especially the assimilation by plankton. The lowest dissolved concentrations of these metals are at the surface of the ocean. So that you're aware, they are assimilated by the plankton. As a dissolution of a decomposition, which is occur at greater place, greater depth. Yeah. We see the periodical table, Mendeleev periodical table, Henry's mostly periodical table, and Devening periodical table, Seaborg periodical table, modern periodical table, and Benfey's spatial spiral periodic table, Bohr model, classification of elements, let us see. Classification method, classification groups, classification period, classification in blocks, metals and metallites, electron configuration, atomic radii, ionization energy, electron negativity, electron affinity, metallic character. We see that. Yeah. The historical history of a periodical table. Versions were published. The numerous rectangular variations and other periodical tables format have been developed. The development of a modern quantum mechanical theories of electronic configuration within atoms, it becomes apparent each period. The Mendel's profile table is a Russian chemist Dmitry Mendeleev was the first published periodic table in 1869. In a periodic table, yeah. Yeah, in a periodical table, actually, it was divided, arranged. The columns are called a group, and the rows we are calling as a periods. Periods and those the columns numbered up to 1 to 18 is corresponding with the element of the state. And he also predicted the some properties of unidentified elements that were expected to fill gaps in the table. The Henry's Moseley's periodic table. In 1913, British chemist Henry Moseley proposed a new periodical table with using of atomic number instead of atomic mass by organizing the principle. Henry confirmed that the integer count of the nuclear charge is identical to the proton count and it determines the values of atomic number of each element. And after that, Deming's periodical table and Seaborg's periodical table, and finally we come into the modern periodical table. 1945, Seaborg suggested that a new periodical table is showing anti actinides. It belongs to the second F log series. Before this time, the actinides were thought into the forming a fourth D block row. But Seaborg suggested was found to be corrected and he subsequently won a Nobel Prize in chemistry in the synthesis of actinide elements. Yeah, finally, the modern periodic table it's expanded into it's a longer 32 column form the reinstating of noted of block elements into the natural position between the S and the D blocks. Unlike the 18 column form, the arranger results in there is no interruptions in the sequence of increasing the atomic numbers, so that it will become very easier to see the F log elements in a periodic table. And Bohr model. The Bohr model it shows the atoms as a central nucleus contains a proton and neutrons. Within the electron, in a circular electron shell at a specific distance from the nucleus, similar to planets it's orbiting around the sun. Each electron shell has a different energy level. And with those shells closest to the nucleus and being the lower in energy than those farther from nucleus. The Bohr nuclear model is increased the difficulty to atoms with atomic numbers greater than 137. As any element with an atomic number is greater than 137 would require it is an electron to be traveling faster than the speed of a light. Yeah, in the periodic classification of elements, we see that each chemical element has a unique atomic number Z. It's representing the number of protons in its nucleus. Most of the elements differing in numbers. In standard periodical table, we see that the elements which are listed in order, and it is increasing by the number of a Z. The elements which are similar to chemical properties, generally it's a fail into the same group, whether it is settled down in a periodical table or not. Although when we see the F black and some to respect in the D black, the elements in the same period tend to have a similar properties as well as that it is relative easy to predict the chemical properties, whatever we are going to identify by the element. If one knows the properties of an element, around the same we will have to find. As of 2016, the periodical table has confirmed by the 118 elements. From one element that is maybe a hydrogen up to 118 that is a arganesa. 113, 115, 117, and 118, the most recent discoveries were officially confirmed by the IUPAC. IUPAC means it's the International Union of Pure and Applied Chemistry. It was in 2015 December. The proposed names actually niobium, moscovium, tennessine, and agassian, and which are 4 elements. It's giving the numbers 113, 115, 117, and 118. Those were announced by the IUPAC in 2016. Yeah, this is you see here. It's a periodical table of different elements. How they were settled here, and classification methods. In a classification method, a group of a family. It's a vertical column in the periodical table, and groups which is usefully have a more significant periods tense than a period. Under an international naming convention, the groups are numbered numerically 1 to 18. From the leftmost column, the alkali metals, and the rightmost column, it is a noble gases. Just you see in this one. And again, in America, the Roman numericals were followed by their A. If a group, it was in the S or P black or B. If it is a group D, then in place of that, they will use B. The Roman numerical numerals, which are used and corresponded to last digit of today naming convention. The example for this one, the group 4 elements were a group 2. That is we will show that is a 4B. And if 14 elements were in A4A. Okay, in worldwide, as per their convenience, they will give the name according to the international names category. And classification of a blocks, actually it is classified from left to right as F, D, P blocks in a periodical table. The specific regions of the periodical table can be preferred as a blocks, a recognition of the same sequence, and each block it's a name according to the subshell, which is a last electron notionally resides. The S block comprises the first two groups, alkali metals and alkali earth metals, as well as the hydrogen and the helium, it will be there. And P block comprises the 6 groups, which groups 13 to 18 in a IUPAC group numbering, and 3A to 3A American group of a numbering. And classification of a metals and metalloid non-metals. The metals and non-metals, it can be further classified the categories, subcategories, which show the depend on their metallic properties. As per that, they will be classified. The elements which are classified into the major categories of metals, metalloids, and non-metals. According to that, the physical and chemical properties we can study. The metals are generally shiny and highly conducting solids, and that from the alloys with another one salt like ionic compounds, which are it is looking into non-metals. Yeah, periodical trends and the patterns. As per the electronic configuration, atomic radii, ionization energy, electronegativity, and electroaffinity, the characteristics of metallic minerals or elements, which are playing the very important role in periodic trends and the arrangement of elements as per a pattern. Electron configuration. The shell and subshells in a periodic table, which are arranged increasing energy according to the Madelung rule. As per that, they will be occupy the different series. The electron shells, which are arranged, each shell is consisting of one or more subshells. The name we are calling that is SP, DF, and G. As atomic number, if it is increases, the electron progressively fill these shells and subshells more or less according to the Madelung rule or energy. It's ordering shown here. The electron configuration of a neon, for example, if you see 1 S2, 2 S2, 2p6, with atomic number of 10, the neon has 2 electrons enter into the first shell and 8 electrons into the second shell. There are 2 electrons in the subshell and 6 in the p subshell. In a periodic table, the first time an electron occupies the new shell corresponds to the start of each period. The atomic radii. Atomic radii is very across the periodic table. The atomic radii, it is generally decreases along the period of table form. Alkali metals and noble gases, which increase in the down in each group. Ionization energy. Each period it's a begin with at a minimum for the alkali metals and ends at a maximum for a noble gases. The first ionization energy is remove the electron from an atom, and the first ionization energy it is 738 kilojoules per moles, and second ionization energy it is 14,050 kilojoules per moles. Electrons in the closer orbital experience greater for forces. Electronic attraction it will be also there. Electronegativity and electroaffinity. Here the electronegativity is the most tendency of an atom, and it is attracting the shared pair of electrons. And atom electronegativity is affected by both that's maybe it is atomic number and distance between the valence of electron, and also it is related to the nucleus. The higher its electronegativity, it's more than elements attracts than electrons. The theory was proposed by the Linus Pauling in 1932. Electronegativity, if it is increased and passing from left to right along the period and decreases the as per group in a descending order. We know that the fluorine, it is the most electronegativity elements, and next place it is occupied by the chlorine, and the least of element, that is cesium. Yeah, this electroaffinity, I'm not going to detail into that one, but actually we have the composition of a planet and meteorites of Earth. We see that. Actually, we have no time. And again, this outline I'll tell you. The composition of a planets. The planets are in a homogeneous in a composition, and their interiors are different from their surfaces. However, the data on their densities, as per the densities and analogies, the Earth itself provide some guide. One, it is a terrestrial planet. The 4 terrestrial planets that we know, that's Mercury, Venus, Earth, and Mars. These are all called the terrestrial planets, or telluric planets also. Or we may call these are rocky planets also. Because of the planet's maximum, it's consisting of a primarily composition, it's a silicate rock or silicate metals. Within a solar system, these terrestrial planets are close to the sun. What are those? Mercury, Venus, Earth, and Mars are very close to the sun. And again, the composition of these planets, it's having the hydrogen, helium, and water existing of different physical states. And again, if you go into the inner planets, Mercury has no atmosphere. Winner of a planet, Mercury actually doesn't have any atmosphere. And the density, it is similar to that of Earth. And Venus, it is nearest and neighbor, and it has very dense into the atmosphere. And it's consisting of a maximum of carbon dioxide and nitrogen gases. And Mars, it's the next planet beyond the Earth. The clouds and dust storms are observed on the same. Polar frost caps from it will be forming a winter season, and it will disappear in summer. The polar caps are formed within a thin layer of H2O, so that here some solid H2O it is going to form along with some solid carbon dioxide. Carbon dioxide also we can able to see in that area. And next one, it is a giant planets or Jovian planets. The remaining 4 planets here, Jupiter, Saturn, Uranus, and Neptune. These are all called the giant planet, or sometimes we are called Jovian planets. These planets, which collectively up to 99% of mass, it's known to the sun. And it has a gained gases also. Because of the gas, it will be there in the the maximum it is occupied by the gas, so that we are calling that is here gas gains. And the Jupiter is the largest planet in the solar system. It has a 4 large satellite moons. And next one, it is Saturn. It's the second largest planet, and it's a bright ring system. And Pluto actually, it's a celestial snowball with a surface. It's a methane. It has a 3.6 billion miles from the sun. It was first discovered and classified as a planet in the year of 1930. The Pluto was a long considered our solar system's 9th planet. However, International Astronomical Unit reclassified the dwarf planet of Pluto. It was in 2006 year. Yeah, the composition of meteorites. Here, the meteorites depend on their classification. It has 3 classifications. The first one, it is a sideroids or irons. Siderite and irons average composition, it will be 90% of metal in the core. The second one, it is a siderolite or stony irons. It has a 50% of metal and the remaining 50% silica percentage it will be there. And final one, it is the aerolites or stones. These are the three classification we see in meteorites. But actually now, just we have 2 minutes. And again, we'll go into the analytical techniques. Just the outline of analytical techniques I'll tell you. Here, the first one, it is a geochemical prospecting. What it is a geochemical prospecting? What we will do in a geochemical prospecting? The application of a geochemical principles, whatever we are searching for minerals or ore minerals or deposits, there are various techniques we will be used and various principles we will be used to value the ore metals, including with geophysical and geological methods. The simple principle of a geochemical prospecting to search for traces of characteristic components of a potential ore or mineral deposits. And finally, we trace those materials. Finally, we trace those materials and it's ready to excavate. And here we study the dispersion of elements from the source of a rock or from a source, and it's taken place either the form of particles, either maybe it is a liquid and solutions. But also in some time we can see the gases also. But the main forms of dispersion, although in the transportation by ice and the water and air particulates. And problems of a geochemical prospecting and environmental investigating. When we are doing the prospecting, both geochemical prospecting and environmental pollution studies have three basic elements commonly we have to know. One, it is a primary source of supply for chemical elements. Second one, it is a mechanism for the dispersion of elements. Third one, it is a medium for picking up a collection of elements. The types of analysis here. Here there are some principles. It is possible to mode of analysis. One, it is a total analysis, and second one, it is a partial analysis. That is maybe total digestion, and second one, it is a partial digestion. In a total digestion, it is not possible to distinguish between analyte of elements, primarily whether it is present in a medium and elements that supplied into the geological system from the external source by the method of determining of the total elemental count. Example for if you see the X-ray fluorescence, it's one of the best method for to do the total analysis. But even though this technique is used to solve samples practically, but there is no chance apart to do the dilution. The detection capabilities are sometimes insufficient for many geochemical environmental studies. And many other methods we follow that can be used for metallic elements. Example for atomic absorption spectrometry, ICP-MS, inductively coupled plasma, coupled plasma mass spectrometry, and ICP-AES, that is a emission atomic emission spectrometry. And these type of instrumental methods we can use. And if you go into the partial, in a partial, it is introduce the many uncertainties of problems, geochemical and environmental studies. And there are thus many reasons to choosing the analytical technique based on the partial extraction. There are two factors it will be there, especially in importance of relation to the extraction of technique. One, it is the to attack the must is strong enough to bring the secondary supplied elements into the elemental compound to be studied in a solution. And second one, it is the acid attack should be influence on the primary sample material. So the sampling media and sample preparation. Yes, we have there are various type of sampling media we have. That is rocks, oils, water, papers, and all those. Okay. And so for this one, we need the sample preparation also. The rocks, whatever we required, we have to do the prior grinding to analysis, and serious contamination should be avoided from that one. And we use the gate vessels also be recommended for this one. And generally we do the decomposition. Before going to that, the decomposition of the sample must should be take that is a minus 200 mesh sieve. Sometimes if it is a if it is a rock, or sometimes maybe if we go into the science also, we can consider that is a minus 200 mesh size approximation. It is a very required. And we do the after that. The sample is a dump, we can into the clean or a flat surface, and we can flatten and divide into 4 equal parts. We do that is then again once we have to mix all these sample materials, and we can do the 4 equal parts, that is called as a quarter. And then finally we can do the coning, and we do the again weighing the sample whatever requirement to us in a particularly in rock samples. In rock samples, we do 0.5 gram of samples, and or else if you can go into the soils, that is depend on the instrument calibration, and then depend on the instrument uses. Up to we can use that 1 gram also. Blank. The blank is important. It's a need for running the blanks for each set of determination. It's a very important process for analysis. A blank should represent the same quantities of reagents carried through the same procedure as the sample. The purpose of the blanks is mainly to establish detection limit for elements in the procedure, whether in the procedure, and monitor to the procedure whether it is correct or not, or the sample either it is going to be contaminated or not. For the base of this blank, we may get knowledge. Yeah, now I'm stopping here.